Another widely used classification algorithm is called the support vector machines, abbreviated as SVM. It's just a linear algorithm that can be used for both binary and multi-class classification problems. However, SVM can also use SVM kernel to handle nonlinear, act as a nonlinear algorithm, meaning that it can transform input features or features into high dimensional space. In fact, one of the benefits of using SVM is that it can support multidimensional, high dimensional data, right? As a nonlinear function. Okay. So let's look at briefly how it works. So suppose we have two features, right, represented as red data points and blue data points. And let's say we want to project this into a 2D space here, X and Y axis. So we plot this. And what SVM tries to do here is to draw a line, right? So let's say we have 3 lines here, right? So let's say we have L1, L2, and L3. The goal of SVM is to try and find an optimal hyperplane. So these lines are just hyperplanes. Why we call them hyperplanes is because the goal here is to find, a line that has the maximum distance, all right, what we call margin, from the nearest data point near that line. So we can see the middle line here. If we use this as an imaginary example, we can see that this middle line provides the largest distance between the nearest data point here to this line, and also from this data point here to this line. So given this example, we can choose, let's say, line 2 here, right? This line 2 here, we can say, just gives us the optimal hyperplane that linearly separates, these data points. Again, the assumption here, we are using this SVM as a linear algorithm, okay, to linearly separate these two features from each other. Okay, the goal is again to find the maximum. So when maximum distance between the two nearest data points. So this hyperplane, we can call them maximum margin hyperplane or a hard margin, right? Another benefit is that it's memory efficient. Again, by using those support vectors, again, another good advantage is that very effective in high dimensional cases, right? And can also be used for nonlinear, for example, nonlinear high dimensional space. For example, you can draw a curve using the SVM kernel. All right, so let's now look at how to implement this in Python using the sklearn module, right, or library. So we import the module SVM and we import SVC. So if you go to the API reference here, you can see support vector machine. So we click on that and you can see we have all this, right? So in our case here, we want that we can support classification in this case. You can see it supports also, when it supports regression, we call that support vector regression. So you click on this, I can see these are the different parameters. In fact, we can tune it a little bit and see whether it can improve performance, right? So by now here, we just take the default parameters. We don't pass anything. So just take everything as default. We load our data set. We split the data set. Again, we maintain the 80-20% split. Instantiate the classifier, call that SVC underscore CLF. We fit our training data and test data. We predict it on our test data. And then we generate the confusion matrix, or rather we generate the accuracy score, precision score, recall, F1 score. So we run this. We can see now we are paying attention to recall here, right? 45. So it doesn't do very well. Then again, here, again, we can generate the confusion matrix. So what if we make some, changes here? So we can just pass here. So here, if we go here, we can see C, it's just a regularization parameter. So let's, for example, say we want to just change this parameter and put the C as, let's see, we can say, want to pass a parameter here, C. So here we'll just say C equals to maybe 0.1, right? And then we can also change the kernel, or rather we can just by default, I think it's linear, but we can just say here, this is actually a linear, right? In our case here, we just want to use the C parameter, just change the regularization parameter there. So gamma here, just put it at 1. Again, here are all the parameters here. You can see gamma here basically just means the kernel coefficient can either be scale or out of, right? So let's run this again and see how it performs. So with the regularization parameter, we can see there's kind of some improvement here, right? Okay, pass that and generate the confusion matrix again. So with that, we're gonna look at k nearest neighbor as our next algorithm.